So we're going to start chapter 3 today. Obviously nothing that we covered today is going to be on the chapter 2 test coming up on Friday. There will be more new in this chapter than in any chapter so far. And really, as I've indicated last class, you could argue that really grade 11 chemistry starts in this chapter. If you had to pick one word that is arguably the most important word in this course, it would probably be the title of the chapter, namely the mole, okay? A lot of math is going to be attached to this chapter. Most of it will be new, but it's really nothing beyond multiplying and dividing. That's all it is, okay? But what it will harken back to is those dimensional analysis problems that we did back in chapter 1, okay? Look at the terms, very few of which you may recognize. Empirical formula, molarity, molar mass, molar solution, molar volume, mole. Molecular formula compared to empirical formula. Molecular mass, percentage composition. Relative atomic mass, that's what 3.1's about. Standard solution, stoichiometry, STP. The title of this chapter is The Mole, the Central Unit of Chemistry. And this diagram, or versions of it, will be employed repeatedly, not only throughout this chapter, but also a good chunk of chapter 4. Okay? If you look at the warm-up, it might at first glance be something you relegate to the bin of useless, given the fact that Gary wrote it. In other words, what does eggs, milk, and flour got to do with anything associated with chemistry? Well, complete the grocery list by filling in the missing unit. So let's say you go to the store with the grocery list, and it says 1 what? Eggs.
Dozen.
2 what? Milk. Liters. 3 what? Flour. 3 dozen flour? 3 liters of flour? 3 what?
Kilograms.
Louder.
Kilograms.
Why is that here? Well, because that represents the 3 ways we measure and communicate amounts of anything. We count them, we measure their volume, we measure their mass. And if you go back to this little wheel diagram here, look what's on the rim of the wheel. Number of items, mass, and we have 2 entries with volume. And at the center of this wheel is the word mole. The spokes of this wheel are how we get from any place on the rim to any of the other places on the rim. So in other words, if I have volume of a solution, can I somehow get to mass of the solute? Or if I have a number of items, can I somehow get to volume of a solution, or volume of a pure substance, or mass of a substance? I can if I go through this. And the little units you see here are the conversion factors. Moles per liter, items per mole, grams per mole, liters per mole. All right? There's a lot of sections in this chapter. There are 6 sections in this chapter. I can't say with certainty that we'll be through this chapter before Christmas. If we're not, we're not. I'd like to be, but if we're not, we're not. This is a foundational chapter. Not just for the rest of grade 11, but also for a good chunk of grade 12. Okay? Experimental chemistry is essentially figuring out things about matter that can't be observed directly. Which means the majority of what we know about chemistry and the things that make up matter, we've got through indirect evidence. An obvious reason is the building blocks of matter are too small to see. We can't see individual atoms, let alone their component parts, protons, neutrons, and electrons. And that makes chemistry a bit unique among the sciences. The things that we have to study the most carefully are the things we cannot see. So the fact that we know so much about these little things we can't see is pretty amazing. And throughout the history of science, the vast majority of what we've learned about those little things has been indirect. And there are some very clever scientists out there that figured things out, realizing that they couldn't look at what they were studying directly, but they could ask nature questions, and her answers would tell them about those little individual things. The joy of experimental chemistry lies then in figuring out how to figure stuff out. How would I learn about these things if I can't see them, if I can't count them, if I can't measure them directly? Consider the following ingenious method for determining the relative masses of objects without needing to know their actual masses. Mass is the amount of matter. When you say that one object has twice as much mass as another, you're expressing the object's relative mass. Let's say you wanted to determine the mass of a staple and a grain of rice. But the only scale you have available to you isn't sensitive enough to measure the mass of a staple. You put the staple in there, nothing happens. 0 grams. You put the rice grain on, 0 grams. Yet you want to know which of those is heavier and by how much. Well, what if you measured the same number of each? Think of grapes and grapefruits. Let's say a grape has a mass of 5 grams and a grapefruit has a mass of 500 grams. A grapefruit's 100 times as massive as a grape. If I take 2 grapes, each at 5 grams, I have 10 grams. If I take 2 grapefruits, each at 500, I have 1,000 grams. 1,000 divided by 100 is the same as 500 divided by 5. Same thing here. It's just that the individual particles are too small to measure their masses directly. But as long as I measure the same big number of each of them, and they're the same, then the relative masses of those same big numbers would have to be the same as the relative masses of one of each. And this word is no longer in use in the human language. The English language, as far as I know, nifty. I think that went out back in American Graffiti days. Like keen or groovy. Maybe supplant intriguing. The intriguing aspect of this technique is that we don't even need to know how many objects we weigh. We just need to know that the numbers are the same. And that begs the question, how in God's name could you know you're weighing the same number if you don't know what the number is? That's a great question. But it's something we have to figure out how to answer when we're talking about atoms, because we can't see them. And if we can't see them, how is it that we count them? If we can't count them, how do we know we have the same number of each? Okay? The technique for determining relative masses still works even if the items being weighed aren't identical. So let's say we got 100 staples, but some of those staples are a little heavier than the others, some of them are a little lighter. Same with the grains of rice. Maybe some grains of rice are a little heavier or lighter. It doesn't matter. Then the ratio that we get when we compare the masses of the same numbers are just the ratio of the average masses. Now, why do you think he would have to put that in relative to where we're going with respect to atoms? Why does he need to suggest that maybe the atoms of any element are not all the same mass? And by the way, are the atoms of every element all the same mass? Are all chlorine atoms the same mass? Look at the periodic table. It suggests they are. Mass of chlorine, 35.453. And we'll talk in a few minutes about 35.453 what. But what goes into the mass of an atom? Protons, that we agree have a mass of 1. Neutrons have a mass of 1. Electrons are virtually massless. So chlorine got 17 protons. It's got 18 neutrons. That adds to 35. So where does the 0.453 come from? Do we have like a fraction of a proton? Or does that include the mass of the electrons? No. The electron's far too small. So where does that come from? For that matter, where did any of the fractions come from? There's no such thing as a fraction of an atom. Well, that's because no chlorine has that mass. That's the average mass of the naturally occurring isotopes. Now we're going to calculate this later in chapter 5, but as it turns out, about 75% of all the chlorine, 0.75, has 18 neutrons. So 17 protons plus 18 neutrons, 35. 75% of the chlorine has 18 neutrons. 25% of the chlorine has 20 neutrons. So a chlorine atom with 17 protons and 20 neutrons has a mass of 37. And 25% of all the chlorine out there is that. So if we take 0.75, 75% expressed as a decimal, multiplied by the mass of the chlorine atoms that have 18 neutrons, 0.75 times 35, and we add it to 0.25 times 37, the fraction of the chlorine atoms that have 20 neutrons, we get that number. But there's no atom with that number. It's an average, okay? So that's his reference here, okay? And he uses, for example, if a variety of pens weighs 1.52 times as much as the same number of a variety of pencils, then the average mass of these pens is 1.52 times the average mass of these pencils. And notice that he says same number. That's the key. We have to have confidence that what we're comparing are the same numbers. Even if we don't know what the number is, we have to know they're the same. Here's an example of how we would apply to atoms. I don't worry about this. This must be Gary's typical shopping day. You have 2 bags of candy from a bulk food store. And you just see Gary's walking down the aisle in a bulk candy store. A bag of gumdrops and a bag of jujubes. You intend to determine the relative mass of a jujube and a gumdrop by weighing the contents of each bag. What condition is necessary for this to work? Got to have the same number. He doesn't mention that the bags also have to be the same mass, but that's the idea. It's that simple. But let's apply it to atoms. To use the technique just described to determine the relative mass of different types of atoms, chemists needed to know that they were weighing an equal number of different types of atoms. In the early 1800s, chemists discovered that all samples of a given compound have the same mass ratio of their constituent elements. For example, anytime I have 9 grams of water, 8 grams is always oxygen, 1 gram is always hydrogen, 100% of the time. And we know why that is, because the formulas of the compounds are fixed. And when we were talking about the matter method, pure substance, a compound has always the same proportion of each element in it, which means if the numbers are not changing, then the mass ratios are not changing. That's called the law of constant composition. In 1804, John Dalton, who was actually a school teacher, argued that the law of constant composition not only supported the concept of atoms, but also provided their relative masses. So now we're getting into answering the question, how do we know when the numbers are the same? He reasoned that the mass ratios in which different elements combine are the mass ratios of their individual atoms or a simple multiple thereof. So what are the mass ratio of their individual atoms? Well, this is true, that statement is true, as long as the number of atoms of each element in the compound are the same. For example, a chemist carefully heats 0.350 grams of magnesium in a crucible. It's a little porcelain dish that's ceramics made to be heated to very high temperatures. When that's done, that mass of magnesium will react with oxygen in the air to produce that mass of magnesium oxide. Now, Dalton did not know that the formula for magnesium oxide is 1:1. He assumed it was, but he also said, well, if it wasn't 1:1, it would be a simple multiple thereof. But let's say that's the formula for the compound. It tells us in any sample of that compound, however many magnesium atoms I have to have the same number of oxygen atoms, correct? I don't know what that number is. I just know if that's the formula. If I separate those elements, or somehow I have a way to separate the elements, I'm always going to get the same number of magnesium as oxygen, right? Well, look at the data. We start out with 0.350 grams of magnesium. That holds a particular number of magnesium atoms. Then I react it with oxygen, and the compound with that formula has that mass. What isn't magnesium is oxygen, right? So if I take the mass of the compound, where the formula is 1:1, and I subtract it from it the mass of magnesium, I get how much of that compound with a ratio of 1:1 is oxygen. Meaning, however many atoms 0.35 grams of magnesium has in it, 0.230 grams of oxygen has the same number of oxygens in it because it came from that compound. Does that make sense? Now, if I'm confident that the numbers are the same, then the mass ratios of those equal numbers will be the same as the mass ratio of individual atoms. So when I'm, based on this logic, the mass of magnesium in this compound is 0.350 grams. If I divide that by the mass of oxygen, which in this compound represents the same number of oxygen atoms, I have 0.230 grams. And if I do that that division, I get 1.52. Grams disappears. That means when I weigh the same number of magnesium atoms and oxygen atoms, the magnesium always weighs 1.52 times as much. And if the numbers are the same, then that means an atom of magnesium weighs 1.52 times the mass of an oxygen atom. So, or therefore, if you want, mass of a magnesium atom divided by the mass of an oxygen atom equals 1.52. If the mass of magnesium is 1.52 times the mass of oxygen, then I can also write it like this. Mass of magnesium equals 1.52 times the mass of oxygen. Right? And because the numbers are the same, that has to be true. Look in your periodic table. What is the mass of oxygen? It's back of your book. Right? Now, the obvious question is 16.00 what? Or you want to go to more sig figs, 15.9994 what? Well, we can't use grams because an atom's too small. Gary introduces this later, but the units on the periodic table stand for atomic mass units. often abbreviated just lowercase u, okay? So if oxygen is 16 atomic mass units, what's 1 atomic mass unit? Well, chemists had to agree on that. What was gonna be their standard for relative mass? Because this tells us that a mass of an oxygen atom is 16 times as massive as 1 atomic mass unit. Originally, chemists used hydrogen because hydrogen's the lightest element. And they said, okay, let's define 1 atomic mass unit as the mass of a hydrogen atom. Exactly. They have since changed their standard. Now they look at an atom of carbon 12. Remember isotopes from science 10? When I write carbon 12, that means 6 protons, 6 neutrons, right? So chemists have decided that the mass of 1 carbon 12 atom is exactly 12 atomic mass units. So 1 atomic mass unit is 1/12 of that. So 1/12 the mass of a carbon 12 atom is exactly 1 atomic mass unit. Those are the units we use in the periodic table. In other words, all the masses are relative to that, okay? If you multiply 16 by 1.52, what do you get? Do it in your calculator. What's the mass of magnesium in your table? 4.31 maybe? That's how it's done. Do you know how many magnesium atoms are in 0.350 grams? No, you don't. Do you know how many atoms of oxygen are in 0.23 grams? No, you don't. But you do know they're the same because the formula is 1:1. Okay? Now, before the end of the chapter, you'll be able to look at that mass of magnesium and say, therefore, the number of magnesium atoms in this mass is this. Okay? But we're not there yet. So let's pick, what about number 2? A sample of strontium oxide. Notice strontium's in the same family as magnesium, so we shouldn't be surprised that the formula of the oxide is the same, 1:1. It's found to contain 2.683 grams of strontium, 0.490 grams of oxygen. So this is easier than the sample problem because he tells you the mass of each. So when the numbers are the same, when we're comparing the same number of strontium atoms to oxygen atoms, the mass of strontium in this compound is 2.683 grams. And the mass of oxygen in the compound is 0.490. So what do you get when you do that division? It's 2.683 divided by 0.490.
5.47
Okay,
or 4.8.
okay, 5.48. So let's do it the exact way we did it before. Therefore, the mass of strontium has to equal 5.48 times the mass of oxygen. What's the mass of oxygen? 16 atomic mass units times 5.48. Check strontium's atomic mass. Do it on your calculator and check the mass they match. Once again,
That's close. That's
how many strontium atoms is in that mass? It doesn't matter. All it matters is it's the same number of atoms as there are oxygens with that mass, because the compound had the ratio 1:1. Maybe an obvious question is, what if the ratio isn't 1:1? Well, that's not a big deal. We'll fix that soon. Look at number 3. A 4.218 gram sample of daltonium bromide. And you're looking at Dan, you go, I don't know what that element is. Well, there is no element. It's a mystery element, daltonium. But notice the formula is still 1:1. Is decomposed, and we have 0.337 grams of daltonium when the compound had a mass of 4.218. So this is a little closer to the sample problem. So whatever isn't daltonium is obviously bromine, right? So the mass of daltonium, according to this question, is 0.337 grams. And what isn't daltonium has to be bromine. So what's 4.218? That's the compound. Minus 0.337, which is the amount of it that's daltonium. The difference has to be bromine. So when you do that, what's the mass of bromine? 4.218 minus 0.337. What do you get? Feel free to use your calculator, guys, before it gets dark. How much is bromine?
3.88.
3.88. 3.88. Okay. And again, the formula is 1:1. So those masses are for equal numbers of those atoms, right? So what's 3.88 divided by 0.337?
11.52.
11.52.
52.
Okay, let's go with that. So that means that the mass of bromine equals 11.52 times the mass of daltonium, whatever daltonium is. Now, the next question's a bit of a twist. What is the atomic mass of daltonium if the mass of bromine is 79.9? Well, if this is true, does that also not mean that the mass of daltonium has to equal the mass of bromine divided by 11.52? Right? If this is true, then so is this, right? Let's put the numbers in. 79.9 atomic mass units for bromine divided by 11.52. So what mass do we get for daltonium?
6.94.
What's the element? What element does daltonium represent?
Lithium.
Lithium. Does the formula make sense?
Exact.
Yeah, lithium's an alkali metal, always 1 plus. Bromide's a halogen, always 1 minus. So yeah, the element's lithium. So doing it this way makes it pretty simple. But again, what if the ratio is not 1:1? Now, we kind of already did this up here. Determining the relative masses of the basic unit of matter was a remarkable feat. Dalton bridged the gap between the world we experience and the invisible world of atoms by deriving the relative masses of atoms from laboratory observations. But again, how did Dalton know that the formula, for example, of magnesium oxide was 1:1? He didn't. Recall Dalton's qualification, though, okay? Or a simple multiple thereof. In other words, if the formula of magnesium oxide wasn't MgO, then be MgO2 or Mg2O, a simple multiple thereof. Now, in most cases, that is the case. It is a simple multiple thereof. Not always that simple. But let's say, for argument's sake, that that was the formula for magnesium oxide. All right? When we compared the mass of magnesium in this compound to the mass of oxygen, we wouldn't be comparing equal numbers, would we? If that was a formula, then what we'd be finding out was when half as many magnesium atoms are compared to twice the number of magnesium, these are the mass ratios. What would we have to do to the number of magnesium atoms to make sure that their numbers were the same? Well, multiply that by 2. Whatever mass we got for magnesium, if the ratio is 1 to 2, would have to be doubled, because then we have the same number of magnesiums as oxygen. So in a nutshell, whatever we have to do to the element subscript that we have the fewest of to make it the same as the other one, we do the same to the mass. And here's a sample from it. Barium chloride has a mass ratio of 1.934 grams of barium to every gram of chlorine. Now, if the formula was 1 to 1, then that would be the mass of the same number of barium atoms as chlorine. But it's not. That's the mass of half the number of barium atoms compared to chlorine. So what do we have to do to make the barium the same number as the chlorine? Multiply by 2. If we have to multiply the number by 2, we have to multiply the mass by 2. So when the same number of barium and chlorine are compared, then it's not 1.934, that would be 3.868 grams of barium contains the same number of atoms as 1 gram of chlorine. And that's probably easier played out if we look at one of the practice problems. Aluminum iodide has a mass ratio of 1 gram of aluminum to every 14 grams of iodine. Given that the atomic mass of iodine was 126.9 atomic mass units, what is the atomic mass of aluminum if the formula is this or this? Well, it turns out that's the correct formula, so let's go with that. So if I look at those two mass amounts, am I comparing equal numbers if that's the formula? So the mass ratio that I have here is 14.1 grams of iodine for every 1 gram of aluminum, right? But am I comparing equal numbers of atoms here? So when I decompose the compound, that's how much iodine I get, that's for every gram of aluminum. But those numbers aren't equal, are they? What do I have to do to the aluminum to make it the same number of iodine? Multiply by 3. So now I am comparing the same numbers. So instead of 14.1 for every 1 gram, when the numbers are the same, it's 14.1 for every 3 grams. What do I get? What do you get when you do that? What's 14.1 divided by 3? How much? 4.7? So I could rewrite this if I wanted to. Therefore, the mass of iodine, just like we did before, equals 4.7 times the mass of aluminum. Right? But I already know the mass of iodine. I want the mass of aluminum. So if this is true, so is this. Therefore, the mass of aluminum, once I'm sure the numbers I'm comparing are the same, has to equal the mass of iodine divided by 4.7. And Iodine's 126.9, divide by 4.7. And we'll put the units in there. There's no units here, that's just the ratio. And then, yes, that does happen to be the mass of aluminum, 27. Now, this isn't the formula, but what if it was? Follow the same protocol. What do I have to do to the little number in this formula to make it the same as the big number? Because when I do that, then I know I'm comparing equal numbers. What do I have to multiply 2 by to get 3? You guys want your calculator for that? 1.5, right? 3 over 2? Okay, so instead of this being 1 gram for aluminum, in this example, it would be 1.5. 1 times 1.5. If that was the formula, that would be the correct mass ratio when the numbers would be the same. Now, if you did that, you won't get 27 grams for aluminum. That's why I did the first one, because that is the correct ratio. All right? Now, is your mark on this chapter going to rise or fall based on your ability to do this? No. The big picture here is, does the process make sense? Does it make sense to you that we don't need to know what those numbers are? The only thing we need to have confidence in is that they're the same. And we get that from the formulas. Okay? And then the last page of the section is one I'm actually glad he included. And this, one of the things this demonstrates is that in science, very, very, very rarely are major discoveries, advancements, the result of one person's work. Okay? Dalton assumed that atoms combined in the simplest manner possible. He believed that if a pair of elements, A and B, formed only one compound, the formula for the compound would be AB. If they formed a second compound, its formula would be either A2B or AB2. Now, he was well aware that he had no evidence for his rules of simplicity. He acknowledged that. He therefore conceded that some of his formulas and resulting atomic mass determinations might be incorrect, and they weren't, because nature isn't always that simple or that cooperative. As you may recall from earlier science classes, the formulas of ionic compounds are simple ratios, but not quite as simple as Dalton had supposed. Some of them are, but some of them aren't. On September 3rd, 1860, many of Europe's leading chemists met in Karlsruhe, Germany. At this meeting, the Italian chemist, I love this guy's name, it's pronounced Stanislao Cannizzaro, presented a remarkable paper in which he helped solve what Dalton considered to be a mystery associated with atomic masses. In Dalton's book that he wrote in 1808 called A New System of Chemical Philosophy, where he outlined the atomic theory, where he basically brought humankind back to the idea that all matter was composed of tiny little, invisible, indivisible particles called atoms. So he believed that atoms could not be divided into anything small. Based on that belief, Dalton hadn't understood why clear data showed that when 2 particles of hydrogen gas reacted with 1 particle of oxygen gas, we got 2 particles of water vapor. So, according to Dalton, the hydrogen that was reacting was an atom of hydrogen and another atom of hydrogen. So let's just write it like this. 2 atoms of hydrogen would react with 1 particle of oxygen to make 2 particles of water. Well, Dalton said that must be impossible, because that means we would have to divide that atom up in half. The only way we could make 2 waters is if this thing divided in half. And atoms couldn't divide. So he thought this was evidence that maybe the atomic theory was wrong. What Cannizzaro said was, look at it like this. If each hydrogen is diatomic, and each oxygen is diatomic, then what you're making involves no contradiction at all. Okay? The atomic theory still works. The only difference is what's reacting are two particles stuck together. And when Dalton saw that, he's quoted by saying, it was as if a veil has been lifted from my eye. It's one of those aha moments. Of course. Makes perfect sense. So it oftentimes in science takes the collaboration of a number of brilliant revolutionaries to go, okay, this makes sense. The only exception to that is relativity and Einstein. He's the single author of that branch of physics, no one else. He didn't build on anyone else's work, that's all him. And it's very, very rare in science. I had a relativity prof in third year that had, for 20 years, been attempting to find something wrong with Einstein's special theory of relativity. He couldn't. One guy at 25 years old came up with this theory that has proven to be dead solid perfect. And it made predictions that were borne out decades later. And then in 1916, something even weirder, that it's the theory of general relativity. And then you get into curved space and things like that. But yeah, that's one of those rare things in science. But the vast majority of science doesn't work that way. Cannizzaro's paper went on to describe and explain 3 other techniques for determining atomic masses, one for metals, one for liquid or gaseous nonmetals, and one for solid nonmetals. Dalton is called the father of the atomic theory. Well, that's what his book is about. Because he explained how the law of constant composition provided support for the concept of atoms. However, additional methods were required to determine the relative atomic masses, some of them associated with gases. So it's not really difficult to understand if you can measure the mass amounts of, say, 2 solids. Take a solid compound, decompose it. But what if the reactants are gases? And what if the products are gases? How do you then know if you're comparing the same number of gas molecules? In other words, where did this data come from? How did we know that 2 hydrogens reacted with 1 oxygen? That's a good question. And that's courtesy of an Italian chemist we're going to talk about soon, a big name in mole chemistry called Amedeo Avogadro. But that's coming up. Okay? So, as I hoped I would do, that finishes 2-1. I wouldn't worry about the review questions just yet, because you guys have a test to study for. I will not be able to get all of the chem tests marked and onto the report Power School because my marks are due Tuesday morning. Okay? I will, however, have your labs marked by Friday. So they may, the marks may go on Power School before that, but suffice it to say, when you're here writing your test, your lab reports will be over on the side. You can pick them up. For the most part, what I've seen so far, the lab reports are done quite well. A lot of work, for the most part, was put in by a number of people. If any mistakes that were made were just maybe misreading some of the questions, but none of them were serious. And remember I said that next to tests, labs count for the most marks. So when those lab marks are inputted, it's a reasonable assumption that the marks could go up, okay? And any of you that were here for the academic advisory, did you talk to any of the grade 12s about what you're going through now and what they went through last year? They probably confirmed that, yeah, you're not stupid. Just stick with it, things will get better. And because we've only had 1 test, you can't gauge anything about what the course is going to end up being based on 1 test. Part of that's getting used to the course, part of it's used to getting used to me. Part of it's also finding out what you're capable of. And you may not have had to go down that road before. I don't know how many parents I had to say, well, you're getting 95 and everything else, so look, yours is the lowest mark. I went, okay, mine's the lowest mark. I'm not the same as other teachers, chemistry's not the same as any other course. They'll get used to it. But it also means, as I said earlier, you might have to find a gear you didn't know was there. And the ironic thing is that a lot of times the students that are the most worried are the best students. Because they're the students that are used to getting really high marks, say 8, 9, and 10, and all of a sudden they're in a scenario where, now they maybe have to study something a few times before it makes sense, or practice it before they get good at it. Science 10 doesn't really ask that of you. It's not intended to be that way, because everybody has to take it. But if you stick with it, and you keep doing what I tell you, and keep practicing, as common as it is for the first mark to be low, it's equally common for the marks after that to go north. And again, if you doubt that, talk to some of the grade 12 chem students, and they'll confirm it. So, I don't want to inundate you with too much more than that, because you got a test to study for. So let's wrap it up there for today, okay? Some of the questions I was getting in the advisory session some of them were good questions, but some were like, you guys are overthinking some of this. Some of it you can afford to just relax it a bit. I'm not gonna ask you anything I didn't cover, and if you read something that Gary wrote that makes no sense, ignore it. It's not something I'm gonna focus on, okay? And I actually think he did a much better job of chapter 3 than he did chapter 2, so not too many rabbit holes we're gonna go down here.